Welcome friends, I am Tanmoy. This is my channel Chemistry and History of Molecules. Today we are going to learn about hydration of alkene in presence of acid to prepare the alcohol. In our previous video, we have explained about oxymercuration, demercuration, hydrogenation followed by oxidation. In this video, I am going to explain the hydration of alkene using acid from the basic point. So first I will explain the basic and second I will explain this mechanism. And last we will see some other mechanism for other processes for conversion of alkene into alcohol. So let's start. So today we are going to learn the conversion of an alkene to alcohol. So before going to that, let's look at the property of alkene. So this alkene is made by the parallel overlap of two p orbitals. Okay, this is one carbon attached to two hydrogen, this is one carbon attached to, and this is the parallel overlap. This sign is for symmetry. This is the pz, this is the pz. One electron here, one electron here. After their overlap, they produces this pi orbital. Okay, this is the pi orbital. This is the CH2, CH2, and this is the pi orbital. So what happens? This pi reacts with the proton. We know proton H plus is the hydrogen, if removes one electron, that became H plus. Means this moiety has only one proton, no electron. So this H plus is a very strong Lewis acid. Okay. So what happens? This H plus binds with this double bond. Okay. After binding, what produces? It produces a complex. You can consider it's a adduct, or better than complex, the adduct, which is a cationic species. Okay. Okay. This adduct. Now what happens? If we draw it in Lewis lot structure, it will be easier to understand. This, it forms a bond with this H plus. Now what happens? It forms a particular sigma bond with any one of carbon, and let's draw it CH2, CH2. For example, it forms a bond with any one carbon. Since it was H plus, so addition of H plus with a neutral molecule, ultimate molecular charge will be H plus. Okay, fine. Okay. Now where the positive charge resides? Actually, the positive charge resides over this. This results in the formation of carbocation. Why? Previously, this ethane, this carbon was attached to two hydrogen and one carbon. Two hydrogen, one single bond, and here double bond. Now the double bond is not there. It is consumed due to the formation of this bond. So it's ultimately actually a 6-electron species, and so consequently it is electron deficient. As we know, these 6-electron species are Lewis acidic. Okay, so they are electron deficient, so they are in search of electron. So what they do, they try to react with some another electron rich material to form alcohol. And since we are talking about hydration, means water, and if we see this water is a electron rich material, so this oxygen attacks this carbon, and what produces this alcohol. So this is the hydration reaction, and water is added to two carbon while one is H, another is OH. Okay. Okay. So let's discuss about the nature of acid. What acid could be used for this purpose? So first of all, right, we have to use an acid, and that acid must be first strong enough to protonate the double bond, means alkene. And second point, that acid after the removal of its proton will be stable enough. What I mean, for example, let's consider Ha. So it dissociates and it reacts with this alkene to form alkene H complex, and it should be stable enough. Another thing, it will result in an anion, that is a conjugate base. Conjugate base of this acid, and one of the necessary condition that this conjugate base must be stable. Why? If it is not stable, this conjugate base, then it will abstract the proton from here and it will go back, so ultimately no reaction. So to have a reaction, it is necessary to have a stable conjugate base. And to then, what is the criteria of a stable conjugate base? Conjugate base, you can see, it's an excess of charge, means electron is more here. So those material will be stable which can delocalize this electron pair properly. One of the example is hydrogen sulphuric acid, H2SO4. How? If we draw the structure of sulphuric acid, it will be very easier for you to understand. This is the Lewis dot structure of sulphuric acid. And what happens after removal of one proton? It produces bisulfate anion, okay, and proton. And how it is stabilized? This is resonance stabilized, and means I am not writing those lone pairs again. This another is with the above one, and we know if the number of canonical form increases, the stability of that stability of that part is increases, means the stability of this anion increases as the number of resonance structure increases, and these are equivalent canonical forms. These are equivalent, so this is stable. So that problem of us, that whether the conjugate base will be stable or not, this problem is resolved here. And this sulphuric acid is capable to achieve this thing. Okay, now let's do the reaction. Reaction means reaction with alkene and sulphuric acid. What happens? Like I have explained, it reacts with the proton to form, let's consider sulphuric acid as a H plus, HSO4 minus. Reacts to form this CH3, CH2 cation and SO2 OH minus anion. I suggest you people to write in this way, then it will be helpful for you to understand. And what ultimately forms? Ultimately forms this O, O2 OH. So we have understand that the sulphuric acid is capable to convert the ethylene into its corresponding sulfate salt. Okay, this is called ethyl hydrogen sulfate. Why ethyl? Due to this group. Hydrogen due to this. Actually, it's a diacid and it's a single salt, means one proton is also there. That's why hydrogen sulfate. For example, if we write this, what we say? Potassium hydrogen sulfate or potassium bisulfate. This is also ethyl hydrogen sulfate. Okay. What happens after the hydrolysis of this ethyl hydrogen sulfate and distillation? For example, we have pure alcohol. Initially, what we have taken? This is a concentrated sulphuric acid and it is in cold condition for protonation. And second, under distillation in presence of water, this produces this ethanol. How it produces? If we draw the structure of this bisulfate, it will be, sorry, this hydrogen sulfate, it will be clear to you. For example, let's consider this. Okay, so this sulfur is attached with 4 oxygen, so it is delta plus electron deficient, and these all oxygens are delta minus. Okay. Another thing, that there is one resonance possible, that oxygen will donate its electron, it will do. So in this way sulfur reduces electron density, but when there is a proton, so this proton can shift from this side to this side. How? If we draw the canonical form, means here and here, and proton shifts from here to here. What will be the product? There will be a single bond, OH, double bond, O, C2H5. So don't confuse. So this is okay, but don't confuse. Previously 2 double bonds, 2 CH double bond O were anti, right now same direction. It is not like that. Actually it's a tetrahedral molecule. Tetrahedral means this, and center is sulfur. Here previously, for example, let's draw this one. It is hydroxyl. This is OC2H5. This is double bonded oxygen. This is double bonded oxygen. Okay, this is a double bond. BB. This is DB. This is single bond. SB. This is also SB. Okay, so don't get confused. So if changes happen, actually this angle is 109, this also 109, all are 109. So actually no anti or syn, all are remain almost in the similar position. Okay. So what happens? This by ethyl sulfate, ethyl hydrogen sulfate is attacked by water. How? Water molecule, this is a delta positive I told, and water molecule has oxygen which is delta negative. Okay, that's why it attacks here. First it opens up this, it forms a charge, means what I want to say is minus OH, double bond O, OC2H5 and OH2. Due to this attack, oxygen will have a formal positive charge, so just it will release this proton to neutralize its positive charge. Okay. After that it will push. After that it will remain in this stage. Another thing, this can push the electron density back to remove this ethanol. So ultimate product is double bond. You can see that original sulfuric acid came back, and this C2H5O minus is produces, which upon reaction with proton in the reaction medium will produce C2H5OH. I guess you have understood. Okay. This produced sulfuric acid reacts with this ethoxide minus to produce this ethanol moiety. So I guess you have understood this part. Okay. Now we have to discuss about the intermediate produced in the reaction. And what is that intermediate? That intermediate actually is the carbocation. Means the carbon having 6 electrons on it. This is the intermediate. So right now on which we want to focus? This carbocation. Actually this is, since it is the intermediate, so the reaction depends mainly on this C2H5 plus carbocation, means C with 3 attachment. So its stability determines the reaction. How it's stable? For example, R1, R2, R3. So if they donate electron density from here to here, so 6 electron species, here to here, then the electron deficiency will be reduced and carbon will be stable. So how this carbocation could be stable? Actually, I will make a dedicated video on the stability of carbocation. Right now, I will give a brief. First point, it could be stabilized by plus I effect. What do I mean? Plus I effect means donation through the sigma bond. Okay, means for example, it is attached with a carbon which is electron rich. Means this carbon is attached with some groups which is electron rich. So that then this carbon do not have any electron deficiency. Okay, so this will push the electron. Or differently we can say this carbon attached to X, where the electronegativity of carbon is higher, means En of carbon is greater than En of X. Don't confuse this X with halogen. I am not saying that. Okay, then carbon will have delta minus charge, so it can donate. 1 point. Okay. Second, what could be the second part? One is plus I effect, we have explained in brief. Second is hyperconjugation. Actually, both hyperconjugation and plus I effect pursues the same job, but little different way. So don't confuse with plus I effect versus hyperconjugation. Hyperconjugation means, for example, this carbon is attached with hydrogen. Let's consider one hydrogen, rest of these are different. What happens? The sigma bond, I'll draw it again. The sigma bond this hydrogen, sigma looks like this sp3 and hydrogen's 1s. This is the sp3 and this is the 1s of hydrogen produces the sigma bond. Okay, and this is the vacant p orbital. So what happened? They overlaps. In this way, what happened? This bond pair is delocalized between this and this, and ultimately this carbon got electron. And previously it was 6, right now it can enjoy 8 electron. The main factor is, previously it was under a crisis, means 6 electron. Right now it got some more electron, but it doesn't mean that it is similarly stable like that parent carbon, like this. It is not similarly stable like this, but it is somehow stable. So its electron deficiency is reduced somewhat and became somewhat stable. Okay. So, and third point is resonance, means plus R effect. What if the carbon is attached with a heteroatom having some lone pair of electrons? For example, this is plus, this is the p orbital, and oxygen will also have the p orbital, but this is vacant. This is filled and carbon is vacant. So it can donate its electron density and both atoms can stabilize. Since this has octet, this has octet, this is most effective in case of stabilizing the carbocation. This is the most effective. So in this way, this carbocation could be stabilized. So let's give at least one example of each group. Plus I effect, what can do? Tertiary butyl group. Okay, this can induce plus I effect. Hyperconjugation, at least one hydrogen. See, one hydrogen. Or simply example we can say methyl group. Okay, here. And resonance, this C plus OR. One of the example is methoxymethyl cation, OMe CH2 plus. Okay, you will know that methoxymethyl chloride reacts faster with in SN1 as well as SN2. In SN1 carbocation is produced which is stabilized by the conjugation of this. So I will explain later in a separate video. So till now what we have learned, that this carbocation could be stabilized by plus I effect, hyperconjugation and resonance. Okay. So now we have checked the stability of the carbocation. Now let's discuss about another property of carbocation, that is migration or rearrangement. What? Okay. To understand that, let's give an example. What do I mean? Let's take a different alkene with a substituted alkene. What substituted alkene? Let's take tertiary butyl group containing alkene. This is hydrogen, this is hydrogen. And let's give H2SO4. What will happen? H2SO4 will protonate. And what will produce? The sulphuric acid will protonate this position as the carbocation here is stable. Okay. This is methyl, methyl and methyl. So this is, and how this cation is stable? This cation is stabilized by the plus I effect from here, inductive effect, and hyperconjugation from here. Okay. Okay, this is stable. So consequently what happens? In second step, it reacts with water. So the product should be this. So it is expected that the product should be this, but actually it does not produce this. Why? Because this carbocation undergo rearrangement. What type of rearrangement? This methyl group migrates from here to here. Why? Because previously it was a secondary carbocation. Why? Because this carbon atom is attached to two carbon, so it's secondary. What produces after this rearrangement? Okay, let's see. It will be easier, I guess, to draw everything as it is. Then there is a less chance of mistake. Otherwise, you may end up mistake under the tension of the exam hall. Methyl. And what happens? This methyl group went here to here. Let's draw it in a different way. This is, you have understood, and charge came here. And this carbon right now attached with 3 carbons, so it's a tertiary carbocation. Okay, and the stability of carbocation order is tertiary greater than secondary greater than primary. I will explain this factor in details in next video about stability of carbocation. So just for this moment, you keep this thing in your mind. Okay? Okay. So what will happen after that? After that, this will react with water, and water will attach to this center. What will be produced? This methyl OH, and second is hydrogen and 2-methyl. So methyl, here is the hydrogen, there are also 2-methyl. So now see what was expected. Expected hydration was this. Let's draw it properly. Hydrogen here, hydroxyl here. Okay, what we have achieved? We have achieved this. Why? This is due to the rearrangement. So I guess you have understood the effect of rearrangement. Okay. Now we will discuss some other methods for this conversion of alkene to alcohol. So okay, before going into details, I am to give you just trying to make a comment. In case of reaction, for example, last one, which produces tertiary secondary carbocation, will react faster than primary. Means, what do I want to say? For example, that this and this. If we check the reactivity order, this will react faster because it will produce slower primary. It will produce instantly secondary. Ultimately, after rearrangement, will produce tertiary. But instant, and this will instantly produce tertiary carbocation. So this will react faster. Another thing, you keep in mind a trick. For example, if you want to add H plus and OH minus, so that is water in short. What trick you need to remember? That proton will act, in case of this it's a symmetrical, no problem, anywhere you can do. Here proton will be attached to the carbon which has more hydrogens. Okay, this is, and that hydroxyl group will be attached to a position where less hydrogen. Okay, and this is the Markov-Nikov rule. Markov-Nikov rule. So, addition of water to alkene follows the Markov-Nikov's rule. Okay? Okay. I guess you have understood. Reaction condition for the conversion of ethylene. Let's check ethylene. For example, this ethylene could be converted to alcohol with some other methods like phosphoric acid, H3PO4. Phosphoric acid, water, means actually it is steam, 300 degree centigrade and 60 to 70 atm pressure. I will explain. The product is ethanol. Okay, it is gas. Water, since it is steam, it is also gas. Phosphoric acid is solid and it is taken on silica, SiO2 bed. It is taken. Okay, so this reacts and this is liquid. Actually, this is also liquid, but after reaction condition, this is also initially at this condition it is gas, but if you cool down the reaction mixture, this is liquid. Gas to liquid. This is also gas to liquid. Okay. Okay. So, but if you cool down temperature also, this is gas. So, what is the neat reaction is happening? Gas means this ethylene is ultimately getting converted into alcohol, which is liquid. Okay. So, if you create pressure, then gas will be converted into liquid because it consumes more volume, it consumes less volume due to their nature. Means this is gas, this is liquid. So, you have understood the fact of pressure, temperature, because this reaction is exothermic in nature. Okay, this reaction delta H is negative. Okay, delta H negative. So logically, if you reduce temperature according to La-Chatelier principle, if you reduce the temperature according to the La-Chatelier principle, reaction go this side because delta H is negative. But if you reduce the temperature, the rate of reaction will also reduce. So as a compromise condition is this 300 degree. Another thing, if you reduce the temperature below the boiling point of water, then it will not remain as a steam and this reaction is performed under a catalytic bed. I will details explain in a different video about this process. So this is, so 30 degree is a compromised condition, and you can say optimum condition for the conversion of ethane to ethanol. Okay. Now we will check another process. For example, this is called Oxo-process. Oxo-process. I will details explain in another video about this Oxo-process. What happens? Here dicobalt octacarbonyl is used as a catalyst for the conversion of this in presence of carbon monoxide and hydrogen. Okay, what it produces? It produces CH2, sorry, CH3, CH2 and CHO. Because from this name you can know this oxo actually is for means carbonyl. Group is indicated by oxo. So this is formyl group and this carbon is coming from this carbon monoxide. Okay. After that it is reduces in presence of nickel hydrogen. You know that nickel hydrogen is a very good reducing catalyst. So that's why this reduces this aldehyde into alcohol. So this is the product. This is the product in the Oxo-process. Okay? Okay. So these two are the preparation of alcohol from, for example, ethylene gas. There is another one example which produces ethanol in large scale, but this is not directly related to ethylene. That is a biological process where this carbohydrate, for example, this carbohydrate is donated as CH2O. For if you take glucose, that is C6H12O6. Okay, that reacts with microbes, means under microbial condition this carbohydrate reacts and produces ethanol. This is another process for ethanol preparation, industrial and tons and of produces in yearly. And actually in this way the alcohols are produced which we drink, and you know the consequence after drinking this, so I guess you know better than me. So this is the reason behind that happiness, eternal happiness. This is. So this is the end of our video. So if you like my videos, please give a thumbs up to this video, and if you like this video, please share this video with your friends and subscribe my channel Chemistry, the Mystery of Molecule, and God bless you. And finally, one comment: since we have studied lots of ethanol, so you may feel that I need ethanol, so it is better not to drink ethanol larger amount, and it is also not good to drink in summer time. So rest of the thing is on your, because you know how to control yourself for drinking excess ethanol. So be careful. Bye.